Can you see a crystal vibration? Okay. Mm. Uh, well, hi. This is ME 6750 thermoelectric material. Uh, Today, I'm going to kind of a little bit review, then phonon. Just briefly, since we had the midterm. Okay. Okay. I'd like to start with the Boltzmann transport equation, just briefly. So the electron, last time we started talking about the phonon, but I like to today a little bit review about electron and then move on phonon, okay, kind of. So still, electrons, distributions, one of the most important Boltzmann transport equations. So I'm not gonna go detail, but fundamentally, the distribution is time and distance and momentum, very general, so that we have expression and we develop and the equations. This is really difficult, so we had to assume using the electron radiation time, introducing and distribution between the scattering. So this is a assumption we used. Once we use that, and then using some property of electrons called Coulomb forces and the Fermi distributions, and we come up with this. This is so important, and something like electric field. This is external. So another electric fields and then another electric fields. So we know that electric field voltage is associated with the temperature. This is known from the beginning. And this is external. So that what we come up with, so important, electric field actually uh, internally is the gradient of Fermi energy. That's why Fermi energy is important. And the Fermi energy gradient, that is electric field. Okay? So that we're able to formulate the distribution, arbitrary distribution in terms of equilibrium and temperature difference and electric fields and relocation time. Okay, electron. So that we are able to express the current, even current now in terms of distribution, Fermi distribution, and we come up with simple equations. This is part of this. Okay. So we have expression for electrical conductivity, and we use the some formula, asymptotic formula, the integral, this kind of forms in terms of many, this is summation, many series. So we, again, it's a second order. You look at the second order of a gradient. It's so small, so we neglect. Once we like to see the nature of, so with some assumptions. So if we assume the metal, this is a important assumption, then we come up with this, and then neglecting second order, and this is the approximate simple. Okay, so the electrical conductivity in terms of Fermi energy, we have expression, but this is for metal, not the semiconductor. Okay, keep in mind. But still, we can see some important information, although assumption, but some information. What is that? Is electrical conductivity is the Fermi energy. Actually, near the Fermi energy, according to me, near the Fermi energy is most important. So using the Fermi energy, we're able to define the conductivity. Okay. Now the Seebeck, we try to Seebeck. I told you Seebeck is also according to previous temperature gradient. Okay, if the current is 0, so we're able to express using the previous equations the same, and then we come up with this. This is a Mott formula known as. So this is we first time we're able to see expression of Seebeck. So important, because we like to understand what is a Seebeck from the physics or even assumption, metal assumption. Keep in mind, still we assume the metal, and anyhow, So again, Seebeck is the when energy is a Fermi energy at the Fermi energy is important. Look at that. Otherwise, it's all constant. So that we're able to little bit extend, and then another expression in the book near the Fermi energy. So Fermi energy is again important for transport property, thermoelectric. I think this indicate that is even more than that. Seebeck is the density of state. More density of state is is better. But the electron concentration or Hall electron concentration is inversely something, some information. So more electron does not help the Seebeck. And then mobility, mobility is the kind of density of state, inverse and gradient respect to energy. The gradient of the density of state. Some information near the Fermi energy. Okay, so we move on. This is only a metal kind of other forms. You cannot use a semiconductor. So again, a simple assuming metal still develop the uh, electronic thermal conductivity. Conductivity is electronic and lattice. So we try to define the electronic first of all. And eventually today we're gonna look at the lattice. We're gonna look at it today. Okay, but still, let's electronic is just a typical thermal conductivity, whatever, with the temperature and heat flow is electron is moving, just electron is moving, that's the heat flow and etc., using the distribution, Fermi Dirac distribution, and then when we define here at this moment Lorentz number uh, uh, define, and the Lorentz number is electronic thermal conductivity over uh, electrical conductivity. That's the very important. T is constant. So the Lorentz number, if we increase the electrical conductivity, automatically increase because it's a constant. Look at that. Constant, everything is constant, turns out, Lorentz number. So, but it's a very confusing, but that's the Wiedemann-French law for the metal. I keep in mind, they talk about the metal, not the semiconductor, okay? So don't confuse. And electronic thermal conductivity is, we have nice, but still some meaningful, okay, still meaningful, constant, and look at that. The electronic is electrical conductivity and the Seebeck minus. So if Seebeck is large, we can reduce electronic thermal conductivity. That's a very important. So anyhow, we try to have a higher Seebeck, and it's better because a figure of merit is alpha square sigma and k. So k is smaller, the better, something like that. Okay, so this still matter. Okay, now we like to we haven't defined the relocation time because the C electrical conductivity is proportional to the relocation time. Look at that. Look at that. Okay, the mobility relocation time and time. So actually, the electrical conductivity is the directly depending on the relocation time. So important, relocation time. So that it's a lot of research on the relocation time, and something like we figure out relocation time is a power law, power of R, something like that, constant. So energy power to the law, okay? And then the R is depending, there are mechanisms, scattering mechanism, acoustic, minus half is acoustic phonon, 3 second is ionized impurity, 1/2 is a polar optical phonon scattering. There are three scattering. The most important is this, okay? Mostly dominate, not always acoustic phonon scattering. So this scattering time is the time between the sequential scattering. Okay, it's about the 10 to the minus 14. So short. So electron, I think we showed that about time is so short. So here we like to physically understand because the electrons moving create the current, electric current. So the electrons is scattering so short of time. Okay. So although electron is fast, but it's a collision and scatters. It cannot move fast. It all scatters. So electron moving is turns out so slow. The electron, the velocity is almost the light velocity, but the current electron moving is so slow. I think order is a few centimeter per second electron turn because of that. But how come electricity is so fast? Another question. If the electron moving so slow, why electricity is very fast? The wave. the wave moving fast. So electricity moving fast. Okay, the wave. So electron is not moving fast. No way. That's my understanding of electricity. The wave moving fast of almost light speed, a little less than light speed, but very fast electric. So as long as it is connected, wire is so fast, electricity, so fast. Okay. Okay. Now, we define here is electron kinetic energy. We studied from the beginning, but somehow we developed MD, effective mass, density of state, and then used it. Okay, so we assumed this is sometimes close to electron mass, but basically we use the density of state, effective mass, but this mass actually moving electron, let's say MC, conductive, let's say, okay. That is according to, I'm not gonna go detail. We come up with MC is something like that, different compared to density of state. I think a student, you can raise a question because next week I'm gonna give a review, but still I like to a little bit give you a concept. Okay, that's why I'm reviewing a little bit electron. So you can raise a question. So it's come up with the velocity. Actually, we use the velocity of electron is related to the this MC, conductive effective mass. Okay, but we assumed previously, but actually, okay. Now I will talk about later. Now we're back to power law. Power law. Now in terms of reduced Fermi energy, reduced Fermi energy divided by kBT, and then constant. Okay, that is we say constant, and then develop a Fermi integral. Fermi integral is convenient. Using a Fermi integral, we use the tables. So this is actually, we don't have to assume the metal. I think I didn't hear clear. This is, you may assume a semiconductor, because we didn't use the metal assumption. Okay, so from now, the concentration in terms of integral and the electrical conductivity, semiconductor now, and look at that. This is mobility, everything we define, and CVEC. But it's hard to see internal. It's hard. Everything is tight, but it's related to Fermi energy. But this is a semiconductor. You have to use these for semiconductor. Okay, so So we try to simplify assuming metal and wave expression, but don't confuse. Our goal is a semiconductor, this one. So that look at that. Once we talk about lead telluride is semiconductor, so we have to use this expression, and using Fermi integral, and we come up with minus means n-type, plus means p-type. So we understand 106 is much larger than the metal. Metal was one about microvolt K. So it's about 100 times. We like to have higher. According to go back. According to my calculation here, I think this is somewhat important. Look at that. So alpha t, sigma t, it's the same. This is constant. So when the Seebeck is about 150 microvolt K, it's canceled about. So it's the same, and then minus canceled. So electron is almost zero. If about 150, obviously this is a metal assumption, but anyhow, so higher the better, the smaller the better. Thermal conductivity. Some information now. So just a simple calculation. We got 100. Yeah, 100 is good. 100 is not the best, but it turns out good. And yeah, I like to move on. So now relaxation acoustic phonon, and there is some research, and then this is expression of a tower constant. As long as you have a velocity, density, information potential, and etc., etc., and then acoustic energy power to the minus half. Okay, and the polar optical is the 1/2 energy. Okay, and ionized impurity is 2/3. So what is the meaning of acoustic phonon is the electron. Electron is a particle, and the phonons today is a particle. We assume particle. It's not the acoustic phonon, but once it's a lattice phonon, it's so weird. It's moving like a particle. That's why we name it phonon. Electron is a kind of not photon, similar to photon, similar wave particle. So this size is a lattice size is angstrom. They each other scattering. It's a collision. Okay. That's what happens. Okay, now I like to move on. Phonon. Okay. So since the thermoelectric involves electrons, Seebeck, electrical conductivity, thermal conductivity, we have to understand phonon actually. So phonon is a vibration, but lattice size vibration, and also thermal energy. That's the one of the goal of this course. Okay, energy is a wide. There are so many energy: chemical energy, nuclear energy, kinetic energy, potential energy, all kind of energy. Everything is energy. Mass is energy, but particularly thermal energy, we like to understand. This is so important. We like to understand the thermal energy. Okay, students. This is advanced uh, course of thermoelectric, and we talk about the thermal energy. Okay, so you have to clearly understand the thermal energy. And then we discussed, first of all, monatomic, just one type of atoms. So only A, one type, M, everything, number of A. And then we just figure out mathematically. And as usual, we use disperse curve. This is very convenient using a Brillouin zone, because one Brillouin zone has everything up to the boundary. Okay, so actually the next Brillouin zone is the same thing happen. But it cannot allow any transport between the boundary, because this is so small. So we don't consider this is this is it. This is a Brillouin zone. This is boundary. Next is atoms. So most of acoustic, I think acoustic is here. Acoustic. So velocity, sound velocity is linear here. Linear. W over, this is frequency over K. Yes, linear mostly. But near the boundary, near the lattice, it's exaggerating. Okay, most of here acoustic, but very near the boundary is the something we found it mathematically. We found it just we calculate. Any students? Any question?
You've been so rude.
Hello. Do you have a question, student? Turn off the microphone. Turn off the microphone, student. Please. I can hear your noise. Okay, thank you. So this is so important we understand. Most acoustic is related frequency and K wave number, but actually the group velocity is zero. Here is zero. Look at that. It's the slope. Is it turns out the gradient actually near the boundary. So the gradient is zero. So velocity is zero. No, it cannot pass. Okay, near the, that's the real, that's the what happened. But and then what we can analytically do, this is very close. So Debye actually assumed a linear Debye, and then boundary, that's is they call Debye frequency assumption, and then assuming a linear and then calculate. But still, it works very well. That's a very smart idea. Okay. Now, when we do two different atoms, mass M, two different, then so weird. We just use the mass, and we found what is the dispersion curve is something like that. The acoustic, and then there is a weird we call the optical branch is appears. Just a simple mass is indicate, but still, we will assume W Derive. But so what is this? This is so chaotic vibration, not normal. No, not normal. No, we call normal is here is normal vibration. This is normal vibration. This is no optical. We say optical, and this is the nature of electromagnetic wave. Actually, this is create the electromagnetic wave. Anyhow, so we're focusing on that, and then actually one-dimensional, but now it's three-dimensional. I told you if you look at this is longitudinal, and there is two. So longitudinal x, y, z direction is something like that. So two transversal and one longitudinal. Optical also one longitudinal, two transversal, it turns out. So when we look at the real vibration, this is the computation or measurement same. Okay, we understand that. I think that this is what is a material. Lead telluride. Actually, this is a Brilliant zone, three-dimensional. So when we look at it, is really we understand two transition, transverse, and the one longitudinal, and then three optical. Transverse, two transverse, and one longitudinal. It's something like that. Okay, so x direction, kind of k direction, w direction. This is center. Okay, so this is including everything. This is a Brilliant zone. So Brilliant zone represent everything. Usually this is small k. This is a boundary. This is all kind of boundary. Okay, three-dimensional. Brilliant zone boundary. So hopefully we understand. So that's the nature of thermal energy, I believe. And then there is a Bose-Einstein distribution, similar to electron. Okay, statistically, so it's a lot of work, and Nobel Prize. So similar to distribution, and also density of state, phonon, no, not electron, phonon. So I put the G, pH, phonon density of state, G. Still I'm using G in terms of energy, not the energy, but the frequency, same. Frequency is energy, right? So I think angular frequency is 2 pi frequency. So the energy is H, I think, frequency. So that energy is something like that. Frequency is energy. So in terms of energy or frequency, internal energy, now we define internal energy, nothing more than that. E is vibration energy, we define. E is vibration energy. Yeah, E is a vibration. Omega. That's very clear. But there are distribution and some 0 point energy because there is some kind of 0 point energy. I think it's associated with the electron moving around the nucleus. So more than atom. This is atom, but there is some original energy here. Anyhow, that's the energy of a vibration. And so internal energy defined. And still, this is a Dovai approximation. And we figure out the density of state, phonon. And using the integral forms rather than summation, internal energy. And also we know relationship, thermodynamic, internal energy and specific heat. Wow, this is so interesting. So we're able to define specific heat, and we able to expression, and then there's some measurement of the phonon density of state and frequency, prediction and measurement, and the prediction and the Debye cutoff frequency. So this is a real measurement, but the Debye assumption, since it's integral, this is real, but here high frequency is less than the prediction, but the low frequency is more because of optical. This is it turns out now we understand optical. So when you integrate this part, move to this part, so in is a pretty in agreement with the measurement. Turns out that's what we understand. I understand. Nobody showed this. This is my work. Okay. Anyhow, so that we have a nice expression of specific heat. X is this, and the even velocity in velocity in terms of atomic size delta. It's almost lattice mostly, but not always. So even velocity, sound velocity, this is group velocity. Okay. Why? Because there are so many vibrations, so many vibrations. So it forms a group. I told you, it make a group vibration. Okay, something like sound velocity. We assume sound velocity is group vibration, and atomic size. If it is a binary mixture, then using the fractions, and we come out with delta. What is that? Yeah. This is yeah, A and B, and then AB mixture. So we're able to figure out uh, lead, telluride, and delta. This is example of lead. Yeah. This is the example. So we calculate each lead atomic size, telluride, and then binary. This is the binary lattice size, and then we can calculate the velocity, sound velocity. It turns out good agreement with the experiment. So interesting. I compared myself. I'm not relying on the literature. Myself, 5 binary I compared is in good agreement, the sound velocity. Okay. So measurement and this calculation is in good agreement, I believe. And specific heat using the Fermi integral. Again, once it's integral forms, there is a appendix appendix F, the similar using the Derby temperature. Okay, reduce the Derby temperature, and then we got these, and then plug in, and specific heat, and calculate it in terms of kilogram, in terms of mole, either. Sometimes the people use in terms of mole, fine. Then you can convert to mole or kilogram and compare. This is my work. I didn't took any literature. This is my work. I used the magnesium silicide experiment, and then just a prediction. The white temperature, I got the 140, 114 measurement. I got it from literature. And look at that. The prediction and the measurement is so good. Even the early temperature, very early temperature, and then late higher temperature. This is, T laws, power 3 laws. And then here the large is Dupont Petit laws. It's all agreement. Thereby T power 3 laws. Okay. So specific heat you have used in thermodynamic a lot, and that's the property of thermal energy, right? For example, if there is the liquid drum, okay, gallon on gallon over say water. Okay. So in order to increase the 1 degree, so what is the energy is required? Actually, Q. Heat is required. M mass, Cp, temperature initially and finally. So initial, final, whatever temperature, from room temperature to 100, so that M is raw volume, Cp, Ti, T final. Do you think you can calculate the joule? Yes or no? Say something. Do you understand? This is thermodynamic. Somebody say yes. We can calculate the heat.
Yes, sir.
Yeah, very clear. Because the Cp is a thermodynamic property, volume, density, temperature. Then we can calculate heat. That's what we use. That's a Cp. Okay, this is Cp, a Cv. The thermal energy, actually. This is the thermal energy. Now, so this is
சரி ஓகே
ஷவர்மாக்கிங் ஓகேவா
ம்
ஷவர்மாக்கிங் இவன மாதிரி ஒரு ஆர்டர் கேட்டனே அப்படி சரிங்கறாங்க பாரு நீ ஓகே ஏய் நான் வேலையில நான் தின்னுட்டு பேசி போ
Are you done? Okay. Now, the heat flow. Okay. Now we talk about heat flow, the heat transfer. Okay, Q, heat flow is lattice. Now talk about lattice, thermal conductivity, and the temperature gradient. We know that. That's a thermal conduction. We talk about thermal conduction, the heat transfer. So KL is we call thermal conductivity. Everyone knows that conductivity, but actually is a lattice because there is electronic also. So now lattice thermal conductivity we talk about. Okay, so heat flow now, rate of heat flow is a vibration again. Turns out the vibration energy and velocity, sound velocity, and the number of vibration, number of mode, two traditional, one longitudinal, something like that. So simply, we just use it, and energy is look at that frequency and the distribution again, Boltzmann. Okay, Boltzmann. I will skip. Turns out this is now the ligation time for phonon, not the electron. Velocity of phonon, but in terms of temperature gradient. So we plug in and even symbol minus K, and we develop and also using the density of state, and we develop. This is just to develop using Bose-Einstein distribution, and then but still, yes, the ligation time of phonon, and then finally Oh, this is the thermal conductivity. Okay, X is this. So, wow, that's we understand lattice thermal conductivity. Again, the integral is you can use a table or and then you can calculate this. And then turns out this is very important. Very important lattice turns out 1/3 of velocity, and copper is mean pre-pass, and then CV, specific heat. Mean pre-pass. So we have some idea of mean pre-pass. So because of mean pre-pass is velocity and the time, electation time of phonon again. So this is again is a matter of the electation time. Look at that. Electation time is a scattering. So vibration is a scattering, and that is the thermal conductivity. So we like to look at it. What is a scattering mechanism again? Since we have equations, once we figure out the scattering, then we can figure out the thermal conductivity. Okay, so I think actually usually more than relocation time, then summation, inverse of summation. Usually that's the nature. If you're more than one, again we introduce some of scattering mechanism. So in general, in general, uh, in general, this we have to understand. Okay, uh, thermal conductivity and the temperature. If we look at the normal process, normal vibration, it specific heat is something like that. If specific heat and normal vibration, including optical, but it's gotta be something like that. But what happened is something unharmonic, very weird, unharmonic. That's what we call incorrect. Okay, U process is happen, and then this is a real thermal conductivity. This is a real because of unharmonicity and the umkrap and it's almost the same. But anyhow, this is a weird thing happen. So the normal, no, it is. So what happened is the thermal conductivity is still power to 3 is increasing early low temperature and then decrease. That's the nature of thermal conductivity. I think you have to understand. There's a lot of tons of research about the thermal conductivity, tons. The volume 12, the book, and there's so many research about the thermal conductivity. So important. Many application, thermal conductivity. So this is nature. I'd like to show you some, what time? Yeah, example. Um, there might be, uh, I think I have posted super thermal conductivity. I don't know. Let me check. Let me check content, super handout, super. Super thermal conductivity material. You have it actually. So this is what happened. Wow. I think you have, I told you, this is a thermal conductivity. What the unit is weird here, what per centimeter degree. So what centimeter degree is, I think, centimeter 1 meter 100. So if you using 100 meter K, am I right? No, 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 no. So, oh no, this a little careful. Centimeter, meter. So 1 centimeter, 1 meter is 100. So centimeter cancel. What, you're right. What per, okay, yes. So this is a centimeter. 1 centimeter is 100. 1 centimeter is 100 meter per second, something like that. Okay, 100 times. So silicon about 300. Can you read about silicon? What is thermal conductivity? Can you read it for me? It's a 1.0. This is 100 watt meter K. So silicon has 100 watt per meter K thermal conductivity. Okay, I like to go appendix D. There is a thermal conductivity. Do you know that? There is a thermal conductivity. Melting point. Right there. Thermal conductivity here, silicon. Can you read? Silicon is 1.48. The unit is centimeter K. It's very close to what we have, a centimeter K, something like that. So this is a measurement actually. We have about one, but anyhow, it's an uncertainty of reading. Anyhow, the silicon, germanium, whatever. Look at that. The silicon. Do you understand now? So this is the what happened. Thermal conductivity is very high, around 30, 100 degree Kelvin, but the room temperature is decreasing. And the copper, this is the what happened. Thermal conductivity is very high, around 30. Look at that, 1400. Usually, room temperature is 400. Everybody knows copper K is 400 watt meter K. We know that. But if the temperature is low, it's very high. Wow. 400, 1400 superconductivity. So this is another measurement. Yeah. And this is a kind of amorphous. There's a grain size. There is a boundary scattering, not only the other mechanism, but boundary also scatters. So we can control the grinding and grain. We can create the grain, and then we can reduce thermal conductivity if you use this technique, the grain size, and also the tube also is some effect of tube like that. So there's a lot of research how to reduce thermal conductivity using tube or grain size, something like that. Okay. Even silicon room temperature is 100, but if we use the nano size, it can reduce thermal conductivity. Okay. Let's go back. So we understand. And what is a Umkreb process? A little bit Umkreb process. I don't want to go detail, but Umkreb process this is a bullion, not I think it's confusing. Bullion zone. This is a bullion zone. I think two. This is lattice vibration, phonon. Okay, like a particle. So K1 and K2. So according to the physics, the combine, this K1, K2 combine, this is the K3. So inside a bullion zone, this is okay. But when the K1, K2 the combination is greater than billion zone, it's impossible. This is impossible. So this vibration, phonon, it never combine, so does not conserve, rather than these two become K3 inside, it does not conserve. So that is Umkrep, unharmonicity. Do you understand? That's a major, there's a major unharmonicity Umkrep process. That's what happened near the boundary scatters because of no more normal conserve. The momentum does not conserve. The velocity is a vector. The momentum or whatever k, 2k does not want to become 3, no conserve because of Umkrep. Okay, that's very important. That's what happened. That's what happened. So that that is Umkrep is there is expression Umkrep U. There's expression. Once you have this value, Na is Avogadro number, and beta is I think you can use two assumption. Otherwise, MAV is mass binary. Delta is atomic mass. What do you think zeta V? Answer. What is the zeta V here? Come on. Temperature. What temperature? No one answer.
Room temperature?
What is name of zeta T? If you don't,
W temperature, however you
yes,
pronounce it.
yes, Devi temperature, okay? Dubai temperature or Devi temperature is very important. Devi temperature you can find here, D, somewhere Dubai temperature is, you can find. Hmm? 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 Yeah, Dubai temperature, I'm sorry, there is a Dubai temperature, yeah. Yeah, silicon is a 645 Dubai temperature. Okay, you can find it. I'm sorry, I lost it. Yeah, sorry about that. So Dubai temperature, and then you can calculate Uncrep electration time, and the other is also, but you can calculate as long as you can calculate. But if you assume uncrep, only use this. This is assumption. If you assume uncrep, but there are two even boundary scattering. I told you there is a scattering boundary. So when I look at some weighted phonon, this is phonon relocation time, frequency, and uncrep. This is uncrep, and the other is electron phonon, and the point defect, some, you can see that. So 3 is Matisse rules, okay? So total combined is summation of all individual. This is a Matthissian rules. So when I compute, this is my work, actually my work. This is a lead telluride, is a measurement experiment. And then I calculated the lattice and electronic, lattice and electronic combined together. Look at that. So in this case, almost half is electron, half is lattice, total is this. This is a beautiful theory to understand thermal energy, thermal conduction, electrical contribution, lattice contribution. I think this is the homework. I like your homework. Where did I put my homework? I will announce homework later, so you can look up the e-learning, some small problem, and then some calculation problem. I will post later. Okay. Any question? I'm done. So this is so important. You have to work hard, and next week I'm gonna a little bit move on, and then I'm gonna give you final review. Okay, final review. So otherwise, thank you for your attention. Bye bye.
Yes, sir. Bye.
Bye bye. Thank you. Have a nice weekend.
Bye, sir.